So Riemann sums and area under the curve. So for this, we have the kind of like the general formula for the area under the curve. We have the summations of f of x sub k times delta x for k is equal to 0 to n minus 1. This is the lab endpoint approximations. And you can also have the formula for the right endpoint approximations as the summations of f of x sub k times delta x for k going from 1 to capital N. So I say this is the right endpoint approximations. For delta x is of course equal to b minus a over capital N, for n is the number of rectangles or the number of subintervals that you want to divide the interval from a to b. And x sub k is equal to a plus k times delta x. So the definite integral is actually coming from the idea that the more rectangles we have, the better approximations we're going to get. Because of that idea, we want to increase the number of rectangles up to a very big number. And usually when you have a very big number, you tend to go to infinity. So that is the idea of definite integral. So you basically take the limit of the Riemann sum for k going from 1 to n, and you increase n to up to infinity. Formula a little complicated. However, if you just analyze this particular formula, you can see that delta x is the width of the rectangle. You can calculate using b minus a over n. The function will be also given to you. K is going from 1 to n, and then you just take n go to infinity. Or in other words, this is the area of the rectangles. Right? Find the area of the rectangle, each rectangle, add everything together, and increase the number of rectangles to infinity. So that's what you got. All right, so the limit of the Riemann sum is actually equal to, so this is the notations, this curly notations, right, is indicate integral from a to b, because you want to consider the interval from a to b of the function f of x. Right, the function has to be given to you, dx, to indicate the width of the rectangle, and this dx is very small. Just like the derivative for the notations is d dx, because we want to take the derivative with respect to x. And integral of dx, you want to integrate the function with respect to x. Right? So you want to integrate f of x with respect to, if you have dy, that means you integrate the function with respect to y. So for these notations, these definite integral notations, I'm going to explain it a little bit more. So this integral notations from a to b of f of x dx. In terms of integrals, a is called the lower limit of integrations, and b is the upper limit of integrations. Right, so in general, a and b are called the limit of integrations. F of x, you see right here, f of x here is called the integrand. So some of the notes about definite integral. If limit of the Riemann sum exist, right, so if you find the limit of the Riemann sum right here exist, then you say f is integrable. F of x is integrable on the interval from a to b. And the definite integral that we have is actually equal to the area under the curve, the true value of the area under the curve. Right, so therefore the result when you evaluate the definite integral has to be a number. Results has to be a number. That means the result does not depend on x.
Next, we're going to talk about the properties of definite integral.
Properties of definite integral. Right, so the first one is the integral of a constant. Right. If you have the integral from a to b of c dx, for c is the constant, for an arbitrary constant, constant c, then this is actually equal to c times b minus a. So we can actually visualize this. The function is the horizontal line, c right here, so y equal to c. And remember, the definite integral is used to calculate the area under the curve. And this curve, in this case, y equal to c, bounded between a and b, right? So the definite integral from a to b of c, say that I want to actually evaluate this region. Right, so that is the area under the curve, right? The curve is y equal to c. The region is bounded between c, the x-axis, and the two lines a and b. So the area of this rectangle is a equal to width times height. The width equal to b minus a. The height in this case, c, right? So therefore, that's the integral of constant. It's basically just calculate the area of the rectangle. Right? So I just note here, this one is c, right? So the height is c. The second property is called the constant multiple. You say that if you have the definite integral from a to b of c times f of x for an arbitrary constant c, is actually the same as evaluate the definite integral from a to b of f of x dx and then times c. So that means you can pull the value of c out of the integral. The next property is the sum and difference property. So 3, sum and difference properties. If you have the integral from a to b of f of x plus g of x dx, right? So the integral of the sum is the sum of the integrals. This gives me the integral from a to b of f of x dx plus the integral from a to b of g of x dx. And you can do the same for the difference, right? Integral of difference is difference of the integral. So from a to b of f of x minus g of x dx is equal to the integral from a to b of f of x dx minus the integral from a to b of g of x dx. The fourth property is the additivity. So just say that if you have the definite integral from a to b of f of x dx, this can be rewritten as definite integral from a to c of f of x dx plus the definite integral from c to b of f of x dx. For c, it's between the interval from a to b. So you can actually visualize this additivity if you have some generic curve like this, right? This is y equal to f of x, this is x, this is y, this is a, this is b. And if c is in the middle, let's say c is right here, you can separate this region into smaller regions, two smaller regions, right? And then you can evaluate the definite integral for this regions and also the definite integral for this regions, and then you can add them up together. Number 5, the order of the limit of integrations. Right, so the order of the limits of integrations matter. We define that the positive direction is from left to right, always, right, from left to right. Therefore, the definite integral from a to b, which a is always on the left of b. So the result is going to be a positive number. But if you want to, for some reason, go the other way, if you want to evaluate the integral from b to a, given that b is greater than a, that means you go the reverse directions, then the result is going to be a negative number. So what do I mean by that? Definite integral from a to b of f of x dx is equal to negative of definite integral from b to a. Right, as you can see, the limit of integration gets switched. When you get switched, that means the directions that you want to evaluate the integral change, right? So therefore, you have to add an extra negative in there. Number 6, it's the net area and versus the side area. So the definite integral is used to calculate the area under the curve. When we talk about area, it's supposed to be a positive number, correct? It's always going to be a positive number. But there are cases that you may want to know if the area is below the x-axis or not, right? So consider in this particular case, if you have this functions, it's bounded between a and b, right? So this the regions we want to evaluate the area. I could say this is regions A1, this is regions A2, and this is region A3. Regions A1 is a positive psi area because it's above the x-axis. So A1 positive side area. But for A2 is actually negative psi area because it's actually below the regions, is below the x-axis. So since the regions is below the x-axis. And the last one is A3 is also a positive psi area. Because the regions is above the x-axis. And for the net area, we can combine these three together. So A1 minus A2 plus A3. Because you want to evaluate the integral from a to b of f of x dx. Right? A1 is a positive psi area minus A2 because it's the negative psi area plus A3. Once again, it's the positive psi area. And one last property, if a equal to b, then delta x is equal to 0. Makes sense, right? Because if a is equal to b, delta x is equal to b minus a, b equal to a, delta x is equal to 0. And you have the integral from a to b of f of x dx is equal to the integral from a to a of f of x dx equal to the integral from b to b of f of x dx, and actually equal to 0 because the width is equal to 0. So once again, because the area under the curve, right, is 3, it can be approximated using rectangles. If the width of the rectangle is equal to 0, the area is supposed to be equal to 0 as well. So let's try to do some example here. Try to use the properties that we just learned. Example, if it is known that definite integral from 0 to 10 of f of x dx equal to 17, and definite integral from 0 to 8 of f of x dx is equal to 12, can you find definite integral from 8 to 10 of f of x dx? You can see that the bigger interval is from 0 to 10, right? The two smaller intervals is from 0 to 8 and from 8 to 10. So if you look at the interval here from 0 to 10, 8 in between, right? So the integral from 0 to 10 of f of x dx is equal to the definite integral from 0 to a of f of x dx plus the definite integral from 8 to 10 of f of x dx. Right. So therefore, in order to find the integral from 8 to 10 of f of x dx, you just move things around. So this definite integral from 0 to 10 is equal to 17 minus the definite integral from 0 to a, which is 12. So therefore, the definite integral from 8 to 10 is equal to 5. To the next example. Given that definite integral from -1 to 1 of f of x dx is equal to 2, definite integral from 1 to 5 of f of x dx is equal to 3, the integral from -1 to 1 of g of x dx is equal to 5, and the integral from -1 to 0 of g of x dx equal to 0. Find the following integrals. So you have part A is from integral from -1 to 1 of 2 times f of x plus a g of x dx. All right, first thing first, what is the property I should use here? Once again, go back to the notes and see what you get. Right, so here you have the sum. You can use the sum properties, right? So the definite integral of the sum is the sum of the definite integrals. So you can write this is -1 to 1 of 2 times f of x dx plus the integral from -1 to 1 of g of x dx. So for this step, I use the sum properties. And then for the first integral, I can take the 2 out of the evaluations of the integral. So that is the constant multiple. So I have 2 times the integral from -1 to 1 of f of x dx. And for the second integral, it's from -1 to 1 of g of x dx. So for this step, I use the constant multiple property. So now the job is just to substitute the numbers we have into the calculations. So the definite integral from -1 to 1, what is that equal to? It's equal to 2, so 2 times 2, plus the integral from -1 to 1 of g of x is equal to 5, so this is equal to 9 for the answer. B, you find the definite integral from -1 to 5 of f of x dx. The interval you are considering is from -1 to 5, and you get the problem gives you the interval from -1 to 1 and from 1 to 5. So this is equal to the integral from -1 to 1 of f of x dx plus the integral from 1 to 5 of f of x dx, right? So this is additivity property. From -1 to 1 of f of x dx, that is equal to 2, plus the integral from 1 to 5 of f of x dx is 3, is equal to 5. So that's the answer.
So that's it for me. Please let me know if you have any questions. Thank you.